Good morning, everybody. Last week, finally, of Chem 1. So we've been talking about acids and bases, and last time we saw, interestingly, in something of a review, that the equilibrium constant is a function of temperature. And reactions come to equilibrium. If you change the temperature, that's a perturbation. And you know the Le Chatelier's principle says equilibria will shift with response to perturbations. And in most cases, as you know, the Le Chatelier's principle, the K does not change if you add some products or you add some reactants or increase the pressure or do something to the reaction. K doesn't change. The reaction just adjusts to meet the new, readjusts to meet the equilibrium. When the temperature changes, K does change. And we know K is a function of temperature because, famously, delta G, the free energy, is a function of temperature. And you'll plot the free energy versus temperature on the exam as you've done many times already. So if the free energy is a function of temperature, K is a function of temperature, and you can see in this case, K increases with temperature, K increases with temperature. That means as you increase the temperature, the product side is favored, K larger, favoring the products. And that would also say the reaction is endothermic. So all of those things come together in this chem quiz here, as well as our new definition of pH. So pH is minus the log of this concentration, and the product of the H3O plus and OH minus are always fixed together. They're always equal to Kw. In this case, Kw is 10 to the minus 13. Because it's at 60 degrees as opposed to 10 to the minus 14 at room temperature. So the product of those have to be 10 to the minus 13. And indeed, if you haven't done anything, they have to be equal. If you just have pure water, those concentrations will be equal. That comes from, as you know, a very simple relationship in water. Two water molecules will form that H3O plus OH minus. And basically, it's just the proton hopping from one molecule to another. This one becomes an H3O plus. This one acts as an acid. This one acts as a base. And you'll form H3O plus and OH minus in equal concentrations. So they need to be equal in this case. If you adjust this with other chemicals, you add H pluses, they don't have to be equal. And we know the pH will change as the H3O plus concentration goes up or down. The OH minus concentration will just follow it. If the H3O plus goes up, OH minus goes down. So their product is always the same. And in this case, we've learned that we should manipulate the exponents, because the exponent of the concentration is what we're interested in. The exponent is the pH. You just change the sign. So the exponent of the concentration of H3O plus, in this case, 10 to the minus 6.5. So I didn't do any fancy math. I just realized that these have to be equal. So it's 10 to the minus 6.5 for the H3O plus, and the OH minus is also 10 to the minus 6.5. And it's okay in this to have fractional exponents. And in fact, it makes it easier because we can look directly at this. Those two add up to minus 13. That checks out. And the pH I can read right from the exponent, 6.5. Okay? So those manipulations are relatively straightforward. Oh my goodness. I might lose my voice altogether. 2 more days. And we'll be done. I'll try not to yell so much today. So we got to this point where we could look at different solutions. So a strong acid, a weak acid, water, a weak base, and a strong base. And remember, what's the definition of strong acid? It completely dissociates, gives up all of its protons, all of its H pluses. And in a sense, strong acids are boring. They just blow their whole wad right at the beginning. All the protons come off, and then nothing else interesting happens. It's the weak acids that are interesting. The weak acids hold back. They give a few of their protons away, but then they have a reserve in solution of protons to use later. And we'll see that's what makes them interesting, and strong acids are boring. If I give you an acid and I do not give you an equilibrium, a Ka, that means it's a strong acid. You should assume it dissociates. And I'll probably just write the word strong acid, HCl, or something in there so it's obvious. I don't want you to memorize the strength of acids, but I want you to be able to look at equilibrium constants and say this acid is stronger than that acid. Or if there's no equilibrium constant and I call it a strong acid, it totally dissociates. So every mole of HCl you put in solution gives you a mole of H pluses. Here, every mole of HAC you put in does not give you a mole of H pluses. Just a few of them dissociate. So that pH is higher, fewer H pluses in solution. Here, 10 to the minus 7th is the concentration of H3O plus. Here, H3O plus concentration, 10 to the minus 10. Here, H3O plus concentration, 10 to the minus 13. So I can read off the concentrations directly from the pHs. That's the whole idea, okay? pH is not a complicated thing. We're trying to make it easier. But as many things, in trying to make it easy, sometimes we fail. So we also talked about, it's a language barrier. We also talked about how conductive the solutions will be. And we have these solutions here, so we can look at them, and our idea is that the more ions in solution, the better the conductivity will be, and the brighter our light will be. So this is distilled water here, and here's water with an indicator in it. The indicator is at pretty low concentration. It's ionic, but it's at such low concentration that it doesn't make the light go on. Well, let's just see if the light's working. We'll rinse it off. Over here, we should see bright light. We don't. That's, oh, there we go. Okay, so the light is on. In pure water, we shouldn't see much light at all. And this one isn't exactly pure, as you can tell. I've got the indicator in there. But for the weak acid, you'll notice, I hope you can resolve that. Can I have a shot, alter the camera shot, and just have, there we go. You can see now just a dim light here, and we'll expect a dim light here, weak base, and then bright light for strong base. So that's telling us how many ions have dissociated, and it checks out with our understanding. Strong acid completely dissociates, strong base completely dissociates, these form fewer ions, and 10 to the minus 7th ions is not enough to conduct. So it gets interesting. Let's mix them together. So if we mix solutions 1 and 5, so that's the strong acid and the strong base together, what do we expect will happen? So neutral pH, so we can also see the colors give you the pH. The reds are the low pHs, acidics. These dark blue greens are the basic, and in the middle, the yellowish is neutral. So what do you expect happens if I mix HCl and NaOH together, strong acid, strong base? what do you expect would happen? So let's just take a quick poll on that. Talk to your neighbors and tell me what you think will happen. There's two things to vote on. Let's just vote on the first one. Is it acidic, basic, or neutral after I mix them? So you can vote. You guys go ahead and talk to the group about this. Thank you, Karen. I'm told my mic is not on. Give me the thoughts on that. So many of us, looks like most popular is dim or no light. Bright, dim, no light is the most popular. So let's look at that. We can do the experiment. Ready? And, oh crap, bright light. So neutral does not mean no ions. Neutral means H3O plus concentration, OH minus concentration are equal and 10 to the minus 7. That's what it means. But what else was I putting in that solution? HCl, H plus ions and Cl minus ions. NaOH, Na plus ions, and OH minus ions. Did the Na plus and Cl minus go away? They are still there. That's a salt solution now. It's sodium chloride in neutral water. You could just drink that one and it would be salt water. Don't drink it. But that is just salt water, and salt water, of course, conducts. So don't lose track of the fact that there's other ions in there. Okay? So let's do the same thing with oh, maybe I have that. Maybe I have that. Okay, I have that here. HCl gives you the H3O plus and the Cl minus. That K is very much bigger than 1, we said. Strong acid. This Kb, very much bigger than 1. And recall that it's going to give you Na plus and Cl minus. So adding those together, HCl plus NaOH, the waters cancel out, gives me H2O and NaCl, and sodium chloride completely dissolves in water. So if I put sodium chloride salt on the exam, you have to know if a salt dissolves or not. I mean, you have to know it. There'll be information that you'll be able to tell. You should know. I don't think anybody's too surprised that sodium chloride table salt totally dissolves. You've certainly done the experiment. You've tasted the water in the bay, maybe by accident. Salt water is salty. Most salts, back when I was in I'll do the old man thing. Back in the old days, Dr. Spies at Michigan State made us memorize solubility rules. There are general rules. One of them is sodium salts it doesn't matter what the other ion is. If it's a sodium salt, it probably dissolves all the way. That's one of the rules. I don't make you memorize those rules. I do one of two things. I tell you it's a salt. Maybe I'll tell you it dissolves completely, but I'll only give you a K if it doesn't dissolve all the way, just like the acids. There's a K involved for the dissolution. I will give it to you, and it will be less than 1 because it's not spontaneously dissolving. Okay? So, neutral and bright light. Let's do our little thing. Is this on? Does everybody see that? This will be the test of this. Okay, we'll continue. Let's do 2 and 4. Let's mix those together. So solutions 2 and 4 are mixed. What is the pH after that mixture, and what is the light? Okay, so this one, GSIs do go up and talk to the students, see what they think about mixing the weak acid and weak base. And I'll put some hints up here on top, mixing acids and bases. Okay. If I could have the output of the lectern up here, go ahead and talk about that among yourselves, see what you think. Okay, let's see what you're thinking. I will open the responses. You are thinking. Neutral is very popular. Let's do the experiment and see if that's what actually happens. I'll let you be in suspense for a minute. I keep forgetting to turn the mic on. Somebody remind me when I talk in the group to turn it back on. Let's see what you're thinking about that. Dim light seems very popular, and bright light seems relatively popular as well. Not too many people for no light. So let's see what the actual answer is first, and then see if we can describe it. I understand what the dim light people are saying. You had when you did the strong acid, strong base, you got bright light, and the common characteristic of the acids and bases is they don't dissociate all the way, so you would expect dim light here. Oh, bright light. So we have to go through it and see, and this one, not only is it maybe counterintuitive, it's not even straightforward to go through the equilibrium calculation. We should point out, though, that you probably don't remember this, and I should have put it up on the board. The acid and base strengths, the K for each of them, the Ka for acetic acid and the Kb for ammonia, are about the same. They are about 10 to the minus fifth, both of them. So they're of about equal dissociation constant. They'll produce about the same amount of OH as H plus in solution. But what does that do? So let's go through it. We saw neutral, but we saw bright light. So here is the acid dissociation constant for the acetic acid. And again, I'm just writing the ion as AC minus. We'll look at what it exactly looks like. That has a K. Here is the dissociation constant. Oh, wait, not quite. What have I done here? So if I was going to write Kb, I thought I did it in 2 steps. I have not. If I was going to write Kb for this one, it's not this reaction. This is the base reacting with acid from the water. It's not reacting with H2O to give me OH minuses. Let me just see if I do it. That has a K to it. Okay, I don't. So let me just make absolutely clear. This takes a couple of steps. Oops. Kb is not this. This is not the Kb reaction. This is the reaction of the conjugate acid of this base. The base itself, that reaction is just NH3 plus H2O. This must accept a proton to turn into that. So that gives me NH4 plus OH minus, and it's this that raises the pH. But it produces this. And that brings up a good point. If this is in solution, then this equilibrium must hold as well. So I can use this equilibrium if I'd like, and I just decided to do that. So mixing those two, yes, it makes a combination of these two things. I can look at the combination of those two things as the acid dissociation or the base dissociation. Both have to hold, but I can pick which one I look at. So I just picked the acid. I picked the acid because writing it this way, you can probably anticipate. I'm going to turn this around now, and I'm going to make it 1 over K. And the reason I turned it around, I think you can see, is I want the acid to cancel out and the water to cancel out. And then when I add them together, I have the reaction that I did. I had the acid plus the base going to the 2 ions. And I have to say, how many ions are here? That's what's going to make it a bright light. And how many ions are there? Well, it depends on what? The size of the K, but I can get that now. It's the ratio of Ka1 over Ka2. I hope I wrote them. Oh, I did, good. Ka, 10 to the minus 5. Ka for the acid, it's a very poor acid, but 10 to the minus 10th in the denominator, so that makes this a huge number. Makes K very large for this entire reaction. 10 to the 5th, so yes, I make a lot of ions at equilibrium. I favor high ion concentration at equilibrium there. Those steps are more complicated than you'd be responsible for on the exam. That's too many steps back and forth. Once you're here, you should be able to do it. Add them together and look at the Ks. But to get to that step, that's beyond the Chem 1 that we teach here. In the fall, I would expect you to be able to do that because you'd spend 2 weeks on acids and bases instead of 2 days, and you would have time to do that. Okay, so wonderful. That's it, I think. Anything else in here? This is just a rehash, isn't it? Yeah, this is just a rehash of what we're getting to. We're rehashing the fact that you react this acid and its conjugate base, and you get Kw. So we already went through that. Okay. So let's go to the next thing. The next thing is still acids and bases. I can barely read that over here. It's that one, that one, that one. Okay, so we're going to continue. Now we're going to look at plotting these concentrations. So we'll plot the concentrations of H3O+. To plot the concentrations, this is why we went through that whole trouble to define pH. We want to plot numbers between 1 and 13 and not 1 and 10 to the minus 13. That cannot be plotted on a piece of graph paper. This, 13 steps can. So that is why we went through this whole exercise. Back in the old days, even before my time, you would have log graph paper. So you would have a logarithmic axis that would help you do this. Very, very, very old days. That's like NASA scientists going to the moon in the 60s or 50s days. So, however, if you start with an acid, 0.1 molar, you should be able to do that in your head. 0.1 molar strong acid, pH is 1. Why should you be able to do that in your head? You should be able to do it in your head because that totally dissociates. And if it totally dissociates, it makes 0.1 molar H plus ions. That's the same as H3O plus, right? The proton isn't by itself, it's on the water. Shorthand, sometimes I don't write the whole H3O plus, but that is 10 to the minus 1, isn't it? So the pH is 1. I can do that in my head, not complicated. If I add base, you expect the pH to increase, and it does. And we saw this once you add 1/10 of a mole of base, and that's how much acid you had. You had 0.1 molar in 1 liter, so you have 0.1 moles in that liter. If you had 0.1 moles of the base, you'd use up all your acid that was there. So I'm using up all the acid, making water, and the pH is 7 at the equivalence point. We did that experiment. We took equal moles of acid and base, mixed them together, and we came to pH 7. Okay, that's what the plot would have looked like. This is called the equivalence point. When you've added a mole of base for every mole of acid that were there, you added equivalent amounts of acid and base in the solution. And in this case, it's neutral solution. And you could titrate back the other way. You could add H3O plus and go all the way back to here if you wanted. Same thing if you started with a base and you added acid. You would find the same thing, an equivalence point where you've added a mole of acid for every mole of base that were there, and you'd get to pH 7 at the equivalence point again. But you can read off the concentrations. Any point, if you take nothing else home from Chem 1, every point on this curve is an equilibrium mixture. You can read off the equilibria at any point. This point here, say that's about 12, pH 12. So H plus concentration is 10 to the minus 12. OH minus concentration is 10 to the minus 2. Right? They add up to 10 to the minus 14. Done. Read it right off the curve. It's at equilibrium at that point. Okay? Simple expression there. So, how well do you get this whole logarithmic thing? Let's do this. We're going to mix together. I know you hate it when I do this, but I love to do it. I'm going to mix together the solubility of a salt and the presence of the ion. So these are all sparingly soluble salts. They do not dissolve. There's a K for the dissolving of all of them. And I'm going to titrate. I'm going to add 0.1 molar sodium X, where sodium chloride, sodium bromide, or sodium iodide. That makes tons of those ions. Those sodium salts totally dissolve. So I have tons of chlorine ions, bromine ions, and iodine ions. Now I titrate it with silver ions. I start putting the silver ions in, and they start to go find the Cls and the Brs and the Ags, and the iodines. But these are not very soluble. So when those two things get together, you form the salt, and those concentrations go down, just exactly like a titration. So by looking at the titration curve, which of these is the least soluble salt? If you look at that. So GSIs, get up and let's talk about that one amongst our compadres here. I'll see if I can get you some hints on that to think about. All right, we'll turn on the voting machine. So go ahead and vote on that one if you'd like. And as you might expect, it looks like the two on the outside are popular. I would agree it's got to be one of those. Let's see what you're thinking. Equally distributed between those two. So you need a professional to talk you through it. we don't have a professional, hard to get one, so I will do it. What's going on here? You're looking at titrate. How much? I don't know. How much animation do I have? So px is minus log of the x concentration. Let me just write it down because I don't know what the animation looks like. P of x is minus log of the x concentration. So iodine, for instance. It's the concentration of iodine. So that means that the concentration of iodine ions is 10 to the minus px. Right? That's what we've said. You put the pH. If it was pH, you'd put the pH there. If it's px, you put the px there. It's the negative exponent. So that means here, let's say that's 12, that's 10, and that's 9. So what's the iodine concentration? I probably have this in the animation. Let's just see. No, I'm lame. I think I remade this slide at one time in my life so that this was here. So what is that concentration? If this was 12 and this was 10 and this was 9, well, this concentration is 10 to the minus 12. This concentration is 10 to the minus 10. This concentration is 10 to the minus 9. Whichever is the lowest in concentration would be the least soluble salt in the presence of silver. Okay? It went to the lowest concentration. Why? Because silver removed those ions from solution, and that iodine that used to be in solution is now tied up in this solid at the bottom of the flask. Okay? So you can see what it is. In fact, at equilibrium, those numbers are going to tell you kind of what the K is. That's part of the equilibrium constant. That's one of the concentrations in the equilibrium constant. Okay? For dissolving the salt. So if you understand that, you understand this whole idea of drawing these curves and reading concentrations from the exponent of the concentration. Okay, a solution of HCl is pH 3. You dilute it 10 times. What is the pH? We'll just talk through this together. I'll dilute this 10 times. What is pH? It's minus log of the H3O plus concentration. Minus log of H plus. And again, I'm not writing H3O plus. I'm just writing H plus, same thing. It's the proton. Who gets the proton? Happens to be on water. The proton concentration, H3O plus concentration, this is the pH, the definition of pH. And that makes it make more sense, doesn't it? pH. What's the new pH? Well, I started at pH 3. So my H plus concentration is 10 to the minus 3. I dilute it by a factor of 10. What happens to the H3O plus concentration? Goes down by a factor of 10. So now it's 10 to the minus 4. So what's the pH? 4. Okay, nothing mysterious there, is there? Strong acids, they totally dissociate. They're so boring. Totally dissociate. Those protons just sit there on water, and they never go back onto the conjugate base like they would in a weak base or weak acid. So it's boring. There it is, written out for you in neater handwriting than I can do. But you know what I'm going to do now. Oops. Strong acid and strong base. I'm going to titrate them. How does the titration curve change? We'll talk through this one together. So I'm going to do one titration curve in yellow. So the one that doesn't change. is the titration curve of a strong acid and strong base. Now I'm going to dilute it by a factor of 10 and do it again. Now I'm adding moles of OH minus here. So what is the difference? What's the new titration curve? Well, what features should I be looking for? Well, we already did the first point of the titration curve, didn't we? We said diluted by a factor of 10, and the initial pH is 1 unit higher. It's 4 now. Okay? So that one we got. Equivalence point. I diluted it by a factor of 10, but did I change the total number of moles of acid that were in there? No, I'm adding water. The number of moles of acid are the same, so it'll take me the same number of moles of base to use them up. So the equivalence point should be the same. And near the end here, I'm adding, I'll get to the point where it's all just base, but again, it's 10 times less concentrated than the yellow one. So 10 times less H plus means I come down a unit in pH there. Okay? Lovely. If you understand that, you're really doing this well. Okay. All right, just another example. We'll talk through this one too. Same thing. I've got HCl, 0.1 molar. It's a strong acid, so I know a lot about this. And I'm going to titrate it with 0.1 molar sodium hydroxide and then 0.2 molar sodium hydroxide. And now the axis is going to change twice as fast. As I add by volume, I'm going to change twice as fast. So what happens? It's important to note here, now this is, I'm just going to write it down. This is now volume of base. It's not the total number of moles. I'm adding more concentrated base, so I'm adding the moles faster. More concentrated base along that axis. So in this case, what are the things we should look at? Initial pH is the same. I didn't do any dilution. But I'll reach equivalence point with half the volume because I'm adding the base twice as fast. But that's the only thing that changes. I get to equivalence point faster. Okay? So that's a feature of titration curves. Let's do the weak acid case. That was the strong acid case. This is where it's interesting, and this is the chemistry of life we're going to talk about now. So HA, some weak acid, reacts with base and forms H2O and A minus. This is the reaction of the titration. Note, this is not Ka for HA. This is not that reaction. That's the reaction when you react this with water. This is the reaction happening in the titration. You're taking these HA molecules and reacting them with the base that's coming in. You're converting them into their conjugate base. You're taking that proton off and forming water and the base. So you can do that though, and when you've added 1 mole of base for every mole of acid that you'd have there, you'd get to equivalence point. So you would have an initial pH, the initial pH, an equivalent point pH. So the initial point, there's this mid-region, B, there's this equivalence point, C, and then there's after the equivalent. There's 4 regions to consider. This one, straightforward, you haven't had any base. So you can figure out the pH there just by the concentration of HA. We'll just go through it. I think we go through it. And remember, it's a weak acid. So here, it's mostly HA. It's a weak acid. HA does not dissociate very much. So it's mostly HA. As you go here, you're converting that HA into A minus. So in region B, you have a mixture of the two ions. And then as you keep going, of course, you'll use up all of the HA. And when you get to this point C, it'll be all A minus. Now remember, all is relative. You will have added enough base to use up all your acid. Now you have this in solution, but that's a weak base. It will go back in this direction, and there'll be an equilibrium here. So it doesn't all stay A minus. There's an equilibrium. In fact, this equilibrium holds right there. And as you go D now, once you've used this all up, then the pH is just dominated by the fact that you just keep adding more OH minuses. Okay? Those are the general features. This is the buffer region. This is just going the opposite way, starting with a base and adding strong acid. Okay? Just the kind of reciprocal relationship there. Let's look at it. Let's actually calculate the pH in this region. And now I am going to show you. That's what acetic acid looks like. This is the acidic proton. These protons do not dissociate. It's that proton on the oxygen that dissociates. The carbon-hydrogen bond is very strong. If these protons were acidic, we'd be in big trouble if those were coming off. Only that one comes off. And I abbreviate it here. I abbreviate that whole ion as AC. And there it is, acetate, AC minus. Now your curiosity is fulfilled and you understand what that looks like. Where do you expect the pH to be? Well, between 1 and 7, because it's a weak acid. It's going to be below 7. If I put in 0.1 molar HAC into the solution, the pH is not 1. This concentration indeed is 10 to the minus 1 HAC. And if it were HCl, it would totally dissociate and make 0.1 molar of that and none of that, and then indeed the pH would be 1. But this is a weak acid. It does not shoot everything off in one shot. It holds back. Well, how much does it hold back? We don't know, but let's say a little bit dissociates. That little bit dissociates is X. That would form X molar H3 plus and X molar AC minus. And you've done these calculations before. So we'll go through this quickly. This is just an equilibrium calculation. Again, these are the equilibrium concentrations. A little of that dissociates, makes a little of that and a little of that in equal amounts. So it's X all the way down. This is the one we want to know, that concentration, because that determines the pH. So solve for X. How do I do it? I make it easy. I assume I'm going to put in products over reactants. Okay? So here's the equilibrium expression. Products X times X over reactants 0.1 minus X. But I know K is very small. That means, by definition, this X is very small. Not much of this dissociates. Let's approximate and say on this, compared to 0.1, it's small. So neglect it. You can't neglect it over here because it's a number and it's not relative to anything. So 0.1 minus X is about 0.1. And you do the calculation and you just solve for X. Then it's easy. X squared, multiply that 0.1 over here. That makes that 0.1 times K. That makes that 10 to the minus 6th. And the square root of that about 10 to the minus 3rd. And what is the pH about? It's about 3. But in this case, there's another number there, so it's not exactly 3, and you could put it in your calculator if you'd like. Turns out it's 2.88. You would have guessed that. Okay? So that's the initial, not pH 1, if it were a strong acid. Okay? So let's talk through this. Let's dilute the weak acid now. The solution is pH 3. Oops. That's a typo there, isn't it? This is HAC in solution, not HCl. Can't believe I've probably had this up here a million times. I've never noticed that until this second. So I dilute HAC by a factor of 10. Does the pH go from 3 to 4 like it did in the weak acid case or the strong acid case? Well, if the pH is 3, we're going to talk through this one together. If the pH is 3, indeed, the H3O plus concentration is 10 to the minus 3. That is true. No, you can't make any arguments there. However, it's a weak acid. So how did this concentration get to 10 to the minus 3? You had to put a ton of HA in there. You had to put a lot of it in there to get to pH 3. It doesn't dissociate very much. You put a lot of HA, and most of it is still HA. Just a little of it made H3O plus. So because this is a weak acid, you had to put in lots of this to get up to 10 to the minus 3. This concentration is much higher. So you put in the water, and I will tell you immediately the pH will go from 3 to 4 because you did dilute by a factor of 10. So the pH goes from 3 to 4, but this equilibrium takes over. And what did you do? You did a Le Chatelier's thing, didn't you? You said, I have this, I'm adding water. What happens? More of this can dissociate now. I know there was a lot there. I added a bunch of water, factor of 10. That's going to force the equilibrium, and I'm going to make more of this. So the pH, this concentration, is much greater than 10 to the minus 3. Dilute by a factor of 10. It does initially go up to 10 to the minus 4, but then you have these things in solution, and this dissociates more because of the Le Chatelier thing. So this concentration goes from 10 to the minus 4 to something higher than that, go to something higher than that, and the pH will go down by a bit. So it goes to 4, but then comes back down towards 3 because these protons were held there in the bank, ready to be used in case of emergency. Okay? And here is that emergency. You diluted, but it resisted changing in pH. Didn't go all the way up to 4. 4 immediately, but then, ooh, I'm going to come back towards 3. Okay, let's talk about the equivalence point. Region C, I skipped over B. At equivalence point, you've converted all the acid into base. So now you can say, well, now I have all base, but it, of course, doesn't stay all base. I've converted all to base. You could say instantaneously I get all the base, but then it's a weak base. It'll react with water that's there. And it will form HAC and OH minus. So here's the reaction. What do you expect the pH to be? Well, now it's a solution of weak base. If it's a solution of weak base, the pH is not going to be 7 at equivalence point. It's going to be a weak base. It'll be closer to the basic side. It'll be nearer to 13. But you can do the same calculation, same procedure, say a little of it dissociates, and then plug that in. And in this case, it's a very small k, so it's even a better approximation to say x doesn't matter with respect to 0.1, and you can make the math very easy. And x is 7.5 times 10 to the minus 6. And this one starts to, this number is so big, it's going to get a little farther than 6. This one you would have to put into your calculator and see how far that got from 6. Or express that in base 10, one or the other. Don't worry about that, just put it in your calculator. Okay? So, meats are at equivalence point, not pH 7. higher than pH 7. Why? It's a weak base solution at equivalence point. Weak base is a little higher in pH than pH 7, towards the basic side. Okay? We'll talk through this as well. Titration of each of these, two acids and a base. We're going to titrate them for which is the pH at equivalence point less than 7. So we're going to titrate these acids with, if it's an acid, we'll titrate it with a base. These two are acids. If it's a base, we'll titrate it with an acid. And we're going to ask, when you've added 1 mole of base for every mole of acid, what's the pH? When you've added 1 mole of base for every mole of acid, what's the pH? When you've added 1 mole of acid for every mole of base, what's the pH? And all you have to say, well, if I've added 1 mole of base for every mole of acid, what is there at equilibrium? The conjugate base, Cl minus ions. Cl minus ions do not go back to HCl. That's why that is pH 7 at equilibrium. This one, you take off that proton as you add the strong base. That proton gets removed. At equivalence, you have only the minus ion, but it is a weak base. So it will be, that thing is a weak base. Once you take that proton off, it's the conjugate base. So it'll be slightly basic. Let's go through it. What is present at equivalence point? At equivalence point, you've added 1 mole of OH minus for every mole of HCl you had. You convert it all to Cl plus and H2O. So those two things make H2O. You're left with Cl minus in solution. Cl minus is the conjugate base of a very strong acid. This does not go back at all in this direction. The pH of that one is neutral. We did that experiment. We mixed a strong acid and a strong base. Here, same thing. You convert the weak acid into its conjugate base, but this is a conjugate base. It acts as a base, so the pH will be slightly basic at equivalence point. This one is a base to start with, so you titrate it with acid. You add H3O plus. You'll make NH4 plus, the acid form, and water. So the proton leaves this, goes on this. You're left with water and NH4 plus. But that's the solution of a weak acid. So a solution of a weak acid will have a slightly acidic pH. Okay? So that will have a slightly acidic pH at equilibrium. At the equivalence point. Okay, that's stuff you could do. You could actually do those calculations in, might have time to get to those in discussion on Wednesday, but Wednesday we'll do mostly reviews, so you guys can just tell me if that's what you want to see. Okay, we skipped region B of the titration curve. We did A and C. We skipped B. This is the most important one. That is when you have a mixture of the weak acid and the weak base. And that is the most interesting thing, and this is the most important thing for biological systems. Your body is just loaded with weak acids and weak bases. And what pH they're at determines the ratio of HA to A minus. Let's see what that ratio is. So right in the smack center of this region, the concentrations are equal. You start out with HA and you're converting it into A minus. Here you've added half as much as it takes to get to equilibrium. So you've converted half of this into that. So right smack at half equivalence point, you have equal concentrations of the acid and its conjugate base. So you have the acid and its conjugate base in solution in equal concentrations. So both of these things can happen. You have these things in equal concentration. Now let's consider what happens if you do that. You get to this point. Now let's say I add some more base. Well, I have some more base, no problem. I still have lots of HA. I'll use up that base. This thing would tend to change my pH, but I'm going to convert it to water. Let's say I added some acid, H3O plus. Well, I have plenty of A minus. So I'll use up those protons and convert those to water. So what happens to the pH? It doesn't change that much because you're just using up. You've got plenty in the bank to use up any OHs and any H3 pluses that you add. You just use them up and make water out of them. So the pH changes slowly. Look at that. That's why this region is flat. The pH is changing slowly in that region because you're adding stuff, but you keep making water out of it. Okay? So slow change in pH in that region. It buffers against changes in pH. Buffer means to slow things down, to insulate against change. Buffer means to resist change. Buffers resist change in pH. We can watch it dramatically happen here. We have 3 solutions, well, 2 solutions really. Here is pH 12, sodium hydroxide solution, strong base. Here's pH 12, but we've added to this solution a buffer, equal concentrations, the definition of buffer, equal concentrations of a weak acid and its conjugate base. So this has more stuff in it. It has, we pH'd it to 12, and then we said, we actually did it the other way around, but we pH'd it to 12, and then we added this weak acid and its conjugate base in there in equal concentrations. So this is buffered. This will resist change in pH. This one cannot. Every H plus I add will use up an OH minus and change the pH. I add H3O pluses to this. Those weak base molecules that are in there will use it up and make water out of it. This won't change. Here's just neutral, or this, so we can look at the change. So do we have a camera shot of this? How am I going to acidify them? I'm going to acidify them in kind of a neat way. I'm going to add carbon dioxide. If you add carbon dioxide, we'll carbonate it, but we'll also make it slightly acidic because carbon dioxide will make carbonic acid in the solution. So we're going to add H3O pluses. We're going to make the solution acidic. We're going to try. That means this pH will go down towards the acidic side. What will happen to this one? We're saying this one's buffered and it won't change. So let's give this one a head start in resisting change in pH. Add some H here. And watch what happens. Look at that. Look at the pH change in the unbuffered solution. But same pH in the buffered solution, resisting that change in pH. That is beautiful. Bring up so I get a headshot here on the camera, please. Up to me. Thank you very much. I do this because I think when you signed up for Chem 1, this is what you thought you would see. Somebody with beakers and chemistry happening in real time. Not that kind of chemist. Okay, so we've seen it happen, resisting change in pH. I can quantify this. And I want to point out, you could have predicted that the K was gigantic for both of these. Should I leave it as an exercise? Can somebody tell me why I can predict the K is gigantic for both of these? Do what I often tell you to do. What's the reverse? You know K going this way. It's Ka for that acid. It's the acid reacting with water and forming. And it's a weak acid. So going this way, it sucks. It's 10 to the minus something. So going this way, flip that over, and the K is gigantic. So both of these go strongly this way, and you should have been able to tell me why. Because you recognize the reverse reaction as weak acid or weak base. Not spontaneous in the reverse direction. Very spontaneous. K very much bigger than 1 in the direction I've written it. That means these are great at doing that. They suck up anything you put in there and change it to water. We're not going to go through the math, but you can quantify this. Quantify means put an equation on it. The pH is equal to, in the buffer region, the pKa of the acid plus the log of the ratio of the base to acid concentration. So here it is, the buffer region. Here's half equivalence point. Here's equivalence point. The buffer region is in between the beginning of the titration and the equivalence point. Somewhere in here, the pH changes slowly. And you can see at half equivalence, the pH happens to be numerically equal to the pKa. Super handy. You get one point for free on every titration curve. Because for a titration curve, you have to know K. Give that to you. So if you know K, you know pKa. And you can go right to half equivalence. You can go right to half equivalence and write that one down. Okay, pH has to go through there. Because I'm telling you, this is what the pH does in this region. As these ratios change, it moves away from the pKa. Okay? 1 point for free. In this region, you have more acid. You start out with the acid. You have more acid than base, so that ratio is less than 1. Oh, I forgot. You guys don't know logarithms. Sorry. Why is this the case? Because these two things are equal. If those two things are equal, what is this number? 1. Log of 1 is 10 to the minus 0. Okay? So log of 1, well, you don't need the minus there. Log is 10 to the 0. So our 1 is 10 to the 0. Log of 10 to the 0 is 0. This whole thing is 0 if those concentrations are equal and the pH is the pKa. Sorry, forgot. You guys don't get that in high school anymore. I gotta spoon feed it to you. But you can see if this ratio is less than 1 because there's lots of acid, then this number is a fraction, so the log is less than 1. You subtract away a little from the pKa. Your pHs are lower than your pKa's. And as you might expect, on the other side, now I have more base than acid. And now that number is bigger than 1, log of bigger than 1 is positive, and you have pHs bigger than your pKa's. Okay? Walk through that logic if you cannot follow that because you don't practice with logs very often. There's just some rules of logarithms. Log of 1 is 0, log of a fraction is a negative number, log of a number bigger than 1 is a positive number. Okay? Take those things home to the bank. Need to know them. Okay? So you have base form is more likely here. The acid form is more likely here, of course. And you can sketch out any titration curve now. Let's just do that right now as an exercise. I can sketch out any titration curve I want. Holy mackerel. What's all this? This is discussion from many moons ago. Let's sketch out a titration curve. Here, pH versus, and we'll just do moles of base rather than volume of base because it's easier. And let's say I have an acid. I don't know which one it is, but it's just say HA plus OH, HA plus H2O goes to H3O plus and A minus. These two things are what make the buffer go. But I told you, if the K for this is 10 to the minus 5, I get 1 point on the titration curve for free. Where is it? 1 halfway to the equivalence point. So if this is 0.1 molar HA to start with, then the pH, I could go through the whole calculation, but the pH will be something like 4. I don't, let's not get ahead of ourselves. Let's say we had 0.1 molar here. If this is 0.1 molar and I have a liter of it, and I'm adding moles of base, equivalence point is here, where I've added 0.1 moles of base for the 0.1 moles in 1 liter of acid. So here's the equivalence point. The reason I do that is I want to know where half the equivalence point is. Because at half equivalence, that's my free point in the titration curve. That's the point where the pH equals the pKa. pKa is 5. Minus log of 10 to the minus 5th is 5. So there we go. I get a free one. pH equals pKa equals 5 at half equivalence. That's it. The rest is easy. It starts below that, it goes through that, and then at equivalence point, it does that. But done. Okay? You should be able to do that. Okay, so we'll just summarize. The buffer region goes from the pKa, from pH a little less than the pKa, through pH equals pKa, to pH 1 unit bigger than the pKa. That's the buffer region. And that's how you get the pH at any, this doesn't work for the whole titration curve. It works well in the buffer region. Okay? And dilution of a weak acid doesn't change the pH much at all in the buffer region. If you dilute, and you're in the buffer region, these are about equal, you dilute them both by a factor of 10, the ratio doesn't change. And it's the ratio that determines the pH. So buffers don't even change pH when you dilute them to a great extent. So, very important properties of buffers. That'll allow us to sketch out titration curve. Let's just do it. Here's the weak acid per mole of the strong base. What if I dilute it by a factor of 10? Now we know all those points on the titration curve, don't we? So weak acid, let's just go through it. Weak acid, I dilute it by a factor of 10. We know when you dilute by a factor of 10, the pH immediately goes up by 1 unit, but then comes down. So the pH doesn't change very much in the initial state. And you're going per mole of OH minus. If you go per mole of OH minus, the equivalence point has to stay the same. So 10, dilute by a factor of 10, pH doesn't go up by a whole pH unit because that storehouse of weak acid dissociates more and makes more acid. Equivalence point is equal, but buffer region doesn't change pH much. Resistant to change in pH. pH stays about the same. The equivalence point doesn't change because I'm going per mole of OH minus. I didn't change the number of moles of HAC in there, I just added more water, so I can sketch that out as well. Okay? Those are great questions to have on the exam. Exam will look a lot like the homework. So you should just be looking at the homework, see if you see these kind of questions in the homework. Blah 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 blah. Wait, I'll stop there. If you guys want to snapshot that, because it's the answer to that chem quiz that I didn't do, there it is. So we can pick up here tomorrow. We'll go through a little bit of polyprotic acids, just a tiny bit, and then we'll do a little electrochemistry, and we'll get ready for the final. We'll do a little electrochem on Thursday as well, but Thursday will be mostly chemistry of life and review. So we'll see you Thursday. Good luck studying for the final.